Hey there, I'm Trevor, and today I want to show you a little bit about derivatives. I want you to understand derivatives, and I want it to be pretty fast for you. So I'm going to see if I can get you to understand derivatives in just 10 minutes and make it pretty easy. So let's see. I'm going to get my iPad started, and then I'll start a timer here. There you go. 10 minutes on the clock. Let's see what I can do. Now, the first thing that we're going to have to talk about in order for you to understand derivatives is lines. So we got to go back to when you're, working with lines. I mean, you probably did it. If you're doing calculus now, you probably started working with lines, I don't know, 5 or more years ago. So you've probably done a lot of stuff with lines. But I just want to tell you. So you're familiar probably with the slope. I'm going to do that real quick. We're going to look at the slope of this line. And one thing you might not have thought about in the slopes of lines is, or maybe you did, it's the same everywhere. You can pick any 2 points, and you'll recall this, you pick any 2 points on the line, and then you go, okay, well, how far do I go up to get from one point to the other point, and how far do I go over? And to get the slope, you took the ratio of those. Or you got, rise over run. Or this is the rise, and this is the run. Or even better, delta y over delta x, where delta just means change. So delta y, delta x. Great. Or you may have calculated it from some points. So you said, okay, well that delta y, the change in y is just going to be what the second y value is minus what the first y value is. Nice and easy. Okay, so this was slope. This is slope or m. And you've done this with lots of lines. And the thing about lines is that no matter what 2 points you picked, that ratio was going to be the same. So I picked this point and this point, 2 totally different points. Oops. And I'll end up getting the same slope, the same ratio between them. It never changes for lines. Okay, cool. That's great. Now, for something else, like say a parabola, you probably graphed parabolas, but you probably didn't really think about the slope of a parabola, because that's something you do in calculus. That's not something you do in pre-calculus or when you're first learning how to graph parabolas. So, because the reason is, the slope is different all over the place. It changes. Let me show you actually an animation. It might make it a little bit better. So, see I can move this around. As the point changes, the slope, or how y changes with x, delta y over delta x, changes. So over here, the slope, it's a bigger slope, right? It's greater. Y changes more in ratio to x when the point is over here than it does over here, right? Down here, the slope is like 0. I can get a slope of about 1. I can get really big slopes, depending on what point of the curve I'm interested in. And this is calculus. This is derivatives, because derivatives can help you do that. Now, there's all kinds of nice tricks to make it really easy once you get really good at calculus. But I just want you to understand derivatives really, really deeply. And so we're going to imagine that you had to, solve this problem for yourself before calculus was ever invented. Okay, so here's your issue. You got this function. It's important to you for some reason. It's this f1 of x that I've done is 1.12 times x minus 5 squared plus 3. And for some reason or another, it's really important that you know how y changes with respect to x. What the slope of this tangent is for these different values of x. And you don't have a fancy calculator that's going to do it for you, because calculus hasn't been invented yet. And so that's what we're going to think about. So here's what I want you to imagine. You're thinking about these things, you go, man, I know about lines. I know that I can get the slope between any 2 points really nicely, but this thing's not 2 points, it's just 1 point. How am I going to get the slope of this line at just 1 point? And so you go, oh, well, I guess what I'll do is I'll just start off with what I know, and I know how to get the slope of a line that goes between 2 points. And so you go, okay, well, for any value I want, I can get the slope of a line that goes between 2 points. That's easy. And by the way, you'll notice here, you see that m equals, that's the slope. I put it on there so you can see it really easily. And then as I move this point around, you can see what's happening. So say you pick a point, pretty close. Like say this one's at, make it about 6. Can I get it there? There you go. Oh, close. Anyways, so you say, okay, well, this is the point I'm interested in. Like say I was interested in where x is 6.01 and y is 3.12, and I want to figure out what the slope is. And by the way, note, I got over here, I got this equation of this line, so you can tell right away the slope is 0.24. But remember, we don't have a calculator for it. We don't know. We're inventing calculus ourselves. And so we say, okay, well, I can tell that easily I can calculate the slope between 2 points. And what you notice is, as you bring the 2 points closer and closer together, the slope of the line between the 2 points becomes more and more and more like the slope of the line you're interested in as the 2 points approach each other, right? And you can see that m equals, it's getting closer and closer to the value 0.24, just like the other line, until when the points are right on top of each other, it's 0.24, okay? So that's your plan. You're like, okay, I know how to find slopes. I'm just gonna get these points closer and closer and closer and closer together. If only I had some sort of thing that I knew mathematically in order to accomplish that. Luckily, you took pre-calculus and you do. In pre-calculus, you did this thing called like limits, and now we're going to finally use it. Okay, so we just go to this picture. I'll draw on it a little bit, and we'll see if we can't understand the definition of a derivative. And I got, let's see, about 3 minutes left. So here we go. So remember, what you're trying to do is you're trying to get these points to be pretty close to each other so that the slope here approaches this slope, right? So that they're about the same or exactly the same, preferably, so that you can know exactly what your slope is. That was the whole point. We want to know what the slope is at a certain point. So here's how it's going to work. This is whatever x value that you're interested in. You're interested in knowing the slope of this particular x value. And this, that's not what I want. This is some larger x value. I'll call it x plus h, okay? What h is just some amount that I'm increasing x, okay? And what we want is we want to move this down. What you can think of that as, it's like you're trying to get smaller and smaller values of h, right? Basically, you want h to get tinier and tinier until eventually h is practically 0, and then you're in pretty good shape, because when h is pretty close to 0, right, when h is like pretty close to 0, then the slope of your line is the same as the slope of the tangent line that you're looking for. Okay, so I want you to notice that we're looking for h to go to 0, and then we pretty much got it. Okay, so how does this get us to the definition of a derivative? Well, it's actually pretty easy. So here we go. For a derivative, for the slope, remember that slope was just going to be y2 minus y1 divided by x2 minus x1, right? And this is actually pretty easy to find. If I use function notation, hopefully you're okay with that. If you're not, let me know in the comments. I'll be happy to tell you about function notation. But if we use function notation for this, then this y2 over here, this y2 is going to be f of x plus h. You know, because this was the x plus h, and if I put that into the function f, I should get out the y that I'm looking for. Okay, f of x plus h should give me this y value. And then, let's see, we're going to subtract this other y value of the y value that we're interested in. That's going to be f of our x, f of x right there. And then in the denominator, we'll just have x2, which is x plus h, minus x. Okay, we're setting this up, okay? Now, I'm setting it up this way. You may be going like, why are you using function notation? Like, why are you putting all this stuff in? Because in just a few moments, we're gonna have the limit definition of a derivative, and hopefully it'll make a lot of sense based on, you know, your intuition about the slopes of lines. Okay, so I want you to pay attention to this thing here. Okay, we got this f of x plus h minus f of x over x plus h minus x. Let's write that down. Way we can work with it. Let's see. Ooh, I'm in red now. All right. F of x plus h minus f of x over x plus h minus x. Okay, we can simplify that a little bit. For example, this is like a plus x minus x. Those cancel out. Okay. And so then we get this. And I want you to recall that we got the right value for the slope when h was really small, right? When there wasn't a big difference between those 2 points. And so we want the limit as not x, but as h approaches 0 of this thing here, this f of x plus h minus f of x over h. It's essentially just the limit of the slope as h approaches 0. Now, it wasn't quite 10 minutes. Darn it. I think it was like 12 or something, but I tried. Anyways, so hopefully this was useful to you in understanding the concept of derivatives. If you've got any questions about it at all, throw them down in the comments, and I will definitely reply to you because you'll probably be my only comment. So please, let me know what your questions are. I would love to answer this, any questions you have about this, and any questions you have about any other aspect of calculus or pre-calculus. Okay, so I'm gonna end the video now. Yeah, good luck with calculus. See ya.